Okay, hopefully everybody can hear the sound on this video. If not, hopefully they're reading this sign and getting the video sound up and running. This is a lesson on Chapter 7, Section 2, Part 1 in the Geometry Chapter 7 Study Guide. Now, I'm actually going to start by talking about this concept on our extra pages in the back of the study guide that are labeled notes and the rest of the page is blank. The concept that we're going to talk about is whether you can take three lengths and actually make a triangle out of them. Alright? So, I'm going to make some lengths like so. Okay. So, I have these two paper clips and they're going to represent my two sides of a triangle. Okay, so can I make a triangle out of this side and these two? Well, if I put this one here and this one here in that corner and then bring them together, yep. These three lengths, oops, this one's all up there. This one over. Anyway, these three will make a triangle, right? These three lengths? Absolutely. There we go. How about if that third side gets bigger? Well, let's see. This one's here. And this one's right there. Yep. Looks like that'll work. And then how about this one? Will these three lengths make a triangle? Let's see. This one and this one. Yep. That works. Now, what happens when that third side gets really long? Well, this one has to attach over here to make the corner of the triangle, right? And then this one has to attach over here to make the corner. And they can't reach each other. Oh no, they're not going to make that third corner, right? So basically, when one of these lengths gets really long and the other two shorter lengths can't reach across, I mean, even if they reach straight at each other, they can't touch. They won't be able to make a triangle, right? So basically, that's the idea. When the two short sides, if you add them together, they're not longer than, if they're shorter than, I should say, the longest side. Oops. I don't know what I'm talking about. I'm writing and thinking at the same time about something else. Short side, and oh goodness gracious, long side. Okay. If the two short sides, as I mentioned, cannot reach across the chasm of the long side, they can't reach. You add those two together and they're not going to be able to stretch across. If they're too short, if this amount is too short, as in this example, then you cannot form a triangle. You see? However, up here we have triangles, right? Because the two short sides, or the two other sides, as I was talking about, these are the shorter ones, this was the longest one, right? They were able to kind of connect with one another. So when you added these two lengths together, they were actually longer than the other side. And that means that they can stretch across, they can connect at that to make that third corner. So up here, we had triangles. So when the short sides plus the other shorter side, when you added those two together and that amount was bigger than the long side, then a triangle exists. You can create one. Okay? Alright, so we're going to use this concept to determine whether there actually is a triangle that can be formed or whether one cannot be formed. So I'm going to go back to page 9, down at the bottom. Okay. So, can we have a triangle where the two short sides are 3 and 4 and the long side is 5? Well, if you add 3 plus 4, we'll be able to stretch across the length of 5. Yeah, because these two added together are 7 and the longest side is 5. So that would be yes. The two short sides would be able to meet to make the third corner. Or number 14, the two short sides are 1 and 4 and the longest side is 6. So if these two added together is 5 and the long side is 6, are these two going to be able to stretch across that long side of 6? No. Um, 15. The two short sides here are 17 and 17, and the longest side is 33. So these two add together to be 34, and the long side is 33. As long as these two, when you put them together, are longer than the longest side, then you're going to get a triangle. So you can do this. Just be aware that sometimes they give you the lengths in not a standard order. Like, for example, on number 17, 4 and 39 are the two, 6 and 39 are the two short sides, right? Because 43 is the longest one. So here you'd add these together to get 45. And if the longest side is 43, these are long enough to stretch across 43 because it's bigger. So 17 would be a yes. And then 18, again, they kind of rearrange things. The longest side is not necessarily going to be the one on the end or first or whatever. Just be careful. 7 and 45 are the two shorter sides. And the longest side here is 54. So you would get, 54 on this one. Oops. 7 and 52 over here. So these two, when you put them together, they won't be able to stretch all the way across the length of 54 to meet because they're too short. So this one you wouldn't get a triangle out of. Okay? So basically that's what this theorem says. It says that the two short sides have to be greater than the length of the third side in order for them to come together to make a triangle. Now, the rest of this section has to do with what we do when the answer to this first question is yes. Okay? If we say, hey, yes, like on number 13, number 15, and number 17, yes, we can make a triangle. We can put them together. All three corners will connect, and we're good to go. Okay? When we can do that, when the answer is yes, then we want to figure out what type of triangle we can make. And so we have three types of triangles. Over here on page 8, when the two legs are squared and added together, and that value is equal to the hypotenuse squared, or I should say the longest side squared, then we have a right triangle. We know that from the Pythagorean theorem, right? So you can see on example A, this kind of looks like a right triangle, but we can't be sure because it hasn't been marked in the corner here. Let's test it out. If 6 squared plus 9 squared is equal to 3 root 13 squared, then it will be a right triangle. Let's see. 36 plus 81. I'm not going to put the equal sign there because that's what we're trying to find out. 3 root 13 squared is 3 squared, and then root 13 squared. So this is 9. And then the square root and the square cancel each other out, so you just get 13. These two added together is 117. 9 times 13 is 117. So it turns out that a squared plus b squared is actually equal to c squared. So it turns out that this one is indeed a right triangle. If you did that over here, you wouldn't get a right triangle. A squared, or leg squared plus leg squared, short side squared plus short side squared would not equal the hypotenuse squared. Well, I wonder what type of triangle we would get then. Well, there's two other rules. And it's back here on page 11. I know I'm flipping around a lot in the book, but hopefully cognitively this has good flow for you. Over here on page 11, we have the other two types of triangles that you could get. If a squared plus b squared, if the two short sides squared and added together makes a total that's bigger than the hypotenuse or the longest side squared, or I should say when the longest side squared is smaller than the two short sides squared and added together, then you get something called an acute triangle. A-C-U-T-E, acute. So back in my examples over here in the back of the book, when I had those two paper clips and I had them lined up like this, when the third side was kind of short, then we had a triangle where all three lengths were kind of closer in length to each other. And that triangle is going to have angles that are pretty small. They're going to be smaller than 90 degrees, this triangle here. And that's called an acute triangle. However, when that side got to be much longer in comparison to the other two sides, so like this one, when I put the paper clips like this to make a triangle, when the side got longer than the other two, and these two were the short sides, then you had a really big angle up here at the top. And that angle is bigger than 90 degrees. Do you see? Because these two, rather than being tight up at the top, became really wide at the top. And that's called an obtuse angle. Angles larger than 90 degrees. So you can see when that longest side gets really, really long, like that, then the angle across from that is going to get really, really wide. It's going to widen out. Like from here, it's going to get wider and then really wide. You see the angle at the top? That is called an obtuse triangle. So it all depends on what kind of side length we have for the longest side. So here, the longest side is less than the other two, which means that third side is pretty small. That's like this. That gives you an acute triangle. All the angles are small then. When the long side gets really long, when your longest side, C, squared, has a relationship that's much bigger than the other side, the other two shorter sides, that's more like this, when the longest side is getting really long. That gives you that wide angle up here at the top, and that gives you a triangle that is classified as obtuse. So when I use these calculations, I don't do it in the same order as the Pythagorean theorem. The Pythagorean theorem states, you know, a squared plus b squared equals c squared. It puts the hypotenuse, the longest side, on the right side, and the legs squared and added together on the left. I like to flip it around. I like to put the longest side squared on the left and then the other stuff on the right, because it gives me a better mental picture of exactly what I'm doing. Otherwise, it tends to be confusing, I think. So, going back to this one, let's classify this triangle. Is it a right triangle, which means that leg squared plus leg squared equals our long side squared? Or is it an acute triangle, which means that the hypotenuse is going to be smaller when we square it in comparison to the other two sides squared and added together? Or is it an obtuse triangle, which means that when we square this and compare it to the other two squared and added together, this one is going to be, this left side of the equation will be bigger. So when we set this up, long squared, short squared plus short squared, that's how I always do it. Okay, so this would be 29 squared, and let's see how that compares to 16 squared plus 24 squared. So I get 29 squared is 841, and then if I square these and add them together, this one squared is 256, and this one is 576. When I add those together, I get 832. Okay, so when the long side is bigger when you square it compared to the other ones on the other side, that means we have a really wide angle right here. And that must mean that you have an obtuse triangle. So is it a right triangle? No, it is obtuse. Let's try a few more examples, see if we can classify here. Number one, what type of triangle do we have? Well, first of all, we have to decide whether it actually is a triangle. Determine if the numbers can represent the side lengths of a triangle. So we're going to do a two-step process. First, we're going to use this rule to determine whether a triangle exists, yes, or a triangle does not exist. Then we're going to use our rules of classification, long squared compared to short squared plus short squared, and see what type it is if the answer is yes. So it's like a two-phase process here in determining what we're looking at. So the first part, is it a triangle? Well, these are the two short sides, 5 and 12. If I add those two together, will they be able to stretch all the way across the longest side, which is 13? Well, they add up to 17. So yes, the two short sides can come together. You can have all three sides meet as corners and you can make a triangle. So now that we know that we can make a triangle of these three lengths, let's figure out what type of triangle it is. Well, the longest side is 13, so I'll square that one. And the two short sides are 5 and 12, so I'll square those and add them together. So I get 169, 25, or 5 squared is 25, and 12 squared is 144. So if I add those two together, I get 169. So when these two things are equal, that would be a right triangle. Number two, well, the square root of 8, if you don't know how long that is, you can always just kind of check it out on your calculator. The square root of 8 is about 2.8. So it turns out that is the shortest side, and we need to know that in order to use these theorems, right? So can I make a triangle? If I add approximately 2.8 to 4, will these two be able to stretch across the side length, the longest one of 6? Well, yeah, it's going to be approximately 4.8, or sorry, 6.8, and that is longer than 6. So yes, this will be able to form a triangle. We just don't know what kind yet. Okay, now I'm going to take the other rule, classification. The longest side is 6, so 6 squared. How does that compare to the other two sides squared and then added together? The sum of the square of the other sides, the short sides. Well, I would have 36 here, I would have 16 here, and then 8 squared, square root of 8 squared, the square and the square root would cancel each other out and I'd just get 8. So here I'd have 36, and here I would have 24. So the longest side squared is bigger, much bigger than the other two squared and added together. That's what we get when we have lengths that are long, like this, and the two paper clips were the shorter ones, right? So do you remember when that third side is really long? It creates that angle across from it that's really wide, right up here. That's called an obtuse angle. So this triangle is called an obtuse triangle. And example 3. Can this be a triangle? Well, I think so. When we have 20 plus 21, those are the two shorter sides. Will those two be able to stretch across? When you add them together, that's 41. That would be able to stretch across a length of 28 to form a triangle, yeah. So this one's a triangle. So now we can try to classify it. If the answer to the first step is no, there is no triangle that you can form, then you're done. Just say no triangle can be formed. But if the answer is yes, then we can continue and apply the second relationship here, the second rule that says that if we have the longest side squared, how does that relate to the sum of the squares of the two short sides? Well, 28 squared is 784. This would be 400, and this would be 441, so this would be 841. So it looks like this long side is, when you square it, is really short. It's small, less than the sum of the square of the other two sides. That's what happens when you have that side being relatively short, like this or like this, and the other two sides go up like that. And that means that the angle across from it would be smaller than 90 degrees. And so in this situation, we have an acute triangle. Now, the last example here I'm going to do is number 7, and there's not a whole lot of space left on the page. This is a mastery level example. So if you're doing, if you're aiming to get an A on this quiz, then you're going to definitely want to pay attention to example number 7. Okay? So what I've got here in number 7, they're asking me to graph points A, B, and C and connect them to form a triangle. So please be aware that this counting system on the axes, every square is worth 2, so that's 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, and so on. So just be aware of that as I'm marking these points so you don't get confused. Alright, so negative 3 would be here, positive 5 would be here. There's point A. 0, negative 2 would be here. That's point B. And 4, 1 would be right here. That's C. So if I connect these to make a triangle, they want to know what type of triangle it is. Is it right, acute, or obtuse? Well, according to this rule that we used here in the second phase of these problems, we have to figure out how long the side lengths are first, and then we can apply the rule. So length, we can find that for a line segment as long as we have the points, as long as we have the coordinate values at each end of that line segment. So I'm going to use the distance formula, and I'm going to use the space over here. So forgive me, I'm going to actually, why don't I just wipe that out? So using the distance formula, I'm going to write that, and I'm going to try to find the length between A and B, so that would be the length of this side. I'll try to find the length of segment AC from using these two endpoints, and then finally the length of line segment BC down here. So I'm going to label that as such. The length from A to B would be the square root of the difference of the y values, so that would be negative 3 minus 0 quantity squared, plus the difference of the x values in the same order, so 5 minus negative 2 squared. So that gives me negative 3 squared plus 7 squared, which gives me the square root of 9 plus 49, which equals the square root of 58. Okay, so that's the length of side AB, square root of 58. Length of side BC would be the square root of difference in the y values. I'm sorry, did I say y here? I meant x. These were the difference of the x values, and this is the difference of the y values. There we go. Okay, so the difference of our x values is 0 minus 4 squared, and then plus the difference of the y values, negative 2 minus 1 squared. Alright, so that gives me negative 4 squared plus negative 3 squared. So that's the square root of 16 plus 9, which is the square root of 25, which is just 5. And then finally, the length of the side going from C to A would be the difference in the x values, so 4 minus -3, and then we're going to square that, plus difference in the y values, 1 minus 5 quantity squared. So I would have 7 squared plus -4 squared. So I'd have 49 plus 16, square root of 65. All right, now which one of these three is the longest side? Well, I don't think it's this one because the square root of 65 is close to the square root of 64, which is 8. And so it seems like this would be the longest side, wouldn't it? If you just look at the square root values, wouldn't this be the longest one? The square root of 65 would be bigger than the square root of 58 and the square root of 25, right? So these two must be my short sides, and this must be my long side. So if I compare the longest side squared to the two shorter sides squared and added together, how does that compare? If this number is bigger than this number, then it's an obtuse triangle. If this number is the same as this number, then it's a right triangle. And if this number is smaller than this number, then it's a cute triangle. So I have the square root of 65 squared on this side. I have 5 squared plus the square root of 58 squared on this side. So on this side, the square root and the square cancel each other out, and I just get 65. Here I have 25 plus, same thing here, the square and the square root cancel each other out, so that's 58. So 65, if I add these two together, how does that compare to 83? Well, this one is smaller. That means the longest side is relatively small compared to the other two, which means the angle across from that is pretty small. So that makes this an acute triangle. And that's my answer to number 7.